So folks, in the last video, we really took care of all we needed to say about writing lines in terms of vector equations. I really encourage you to review that video a couple of times to make sure you really understand that big picture. Once we've got that down, we can just go ahead and work all sorts of problems, just like you might have worked in algebra class, where we might ask you about lines and lines being parallel to other lines, or we might talk about how far a point is from a line, etc. So we're going to see some of the consequences of what we've done. Just to recap, though, we said last time that a vector equation of a line passing through a point, in this case I'm using r0, in the direction vector v, would just be that r, vector r, is equal to vector r0, that initial position vector, plus t, some parameter or parameterization, times v, your direction vector. And that's for minus infinity less than t less than infinity. So if you look at any textbook for the equation of a line as a vector equation, that's what you're going to be given. In order to understand what we just looked at, though, you have to really understand that previous video. Okay, so the advantage of the above description, one thing I was careful to do in both Part 3 and Part 4 was I never said that we were in R1 or R2 or R3 or R4 or whatever. And in fact, the advantage of the above description is that it can be extended to any dimension. So let's find an equation of a line passing through these 2 points in R4. So I can't draw this picture, but I can still imagine a line as connecting 2 points in a particular dimensional space and then extending throughout. And so I'd like to go ahead and give an equation to that line. So just as we said before, r is equal to some r0 plus tv. So I could pick either of these 2 points, this point or this point, and call it r0. Let's go ahead and call this point r0. Now we need a direction vector. Well, a direction vector just tells us which direction to head from. Well, we already know that because we know we want to start at this point and eventually head to that point. And so we can use these 2 points to create a direction vector. So if this were point P and this were point Q, we could talk about PQ like this. And how do we give that? Well, that would be as a position vector. The vector, we could write it this way as 4 minus 1, comma, 5 minus 1, comma, negative 3 minus 0, comma, and then 0 minus a minus 2. That's one way we could write the vector. You're going to see me more and more now start writing my vectors this way, especially when I'm dealing with vector lines and vector planes. So this would be the vector 3, 4, negative 3, positive 2 is that direction vector. And so now we're done because I've got my direction vector, which is that vector that takes me from this point to this point. So that's going to be my direction vector v there. And I'm ready to give the equation of this line in R4. So we'd say that r is equal to, there's my initial position vector, 1, 1, 0, negative 2. That's the r0 vector, plus some scalar multiple of my direction vector, which I got from taking the vector that takes me from this point over to this point. And so this would give me 3, 4, minus 3, 2, and we're done. That is the answer to this problem. Oops, with one other thing we need to add for negative infinity less than t less than infinity, telling us what values t can take on there. So let's do this next one. In this case, we're at R2, and we're not asked to come up with a line, but instead a line segment. So if you wanted to draw a picture with this one it is feasible to draw a picture. Let's go ahead and do so. We would have the first point right here, P, is the ordered pair 1, 1, and the point Q, which is the ordered pair negative 1, 2, 3, and I guess we have to go up. 1, 2, 3, 4. So there's the point Q there. And we want to find the line segment that takes us from point Q to point P. Now this is very important, folks. In this problem, I'm kind of teaching you a couple things at once here. I said that I want the line segment to start at Q and end at P. So there's a notion of which way we should travel as our vectors. Remember, we often don't draw this, but as my vectors trace out this line by looking at where their tips lie, As my vectors do that, I want them to go from point Q to point P and not the other way around. Even though I listed P first, I was asked to do the line segment this way, so be careful here. So just as we did before, we're going to build the equation of the line. So our equation of the line is still just R is equal to some R naught plus some TV. And R naught in this case is going to be my initial position. Okay? And my initial position vector, if I wanted to, and I'm going to do this on purpose, folks, so bear with me, because I could take any point that I know on this line to go ahead and start describing the line segment. But I'm going to go ahead and take as my initial position vector the vector 1, 1. Now that's actually a bad choice. Okay? Based on the explanation that I just gave you, I think it would make a lot more sense to take this point Q, as my initial position vector. But I just want to show you something about how these parameterizations work. Okay. The next thing I need is a direction vector v. And so just as we did before, we found the vector going from P to Q. And if we do that, that would be the vector, so we've got P to Q, so it would be minus 3, minus 1, and 4, minus 1. And so this gives me the vector minus 4, comma 3. So I'm now ready to give the entire equation of the line. We would say that R is equal to 1, 1 plus T times minus 4, 3. Now, if I had been more careful initially, and I'd actually done the direction vector from Q to P, and I'd picked as my initial point the vector Q instead of P, then I wouldn't have to be so careful as I am right now. So folks, I want to convince you that we actually have the line that we were describing. So here I've plotted this all in CalcPlot 3D. Here's point P, here's point Q, and then I came up and I gave the vector equation here. Now, entering the vector equation actually involves entering it parametrically. Also, just a defect of CalcPlot 3D is I've got this z of t, so I just set that as 0, and we're just in the xy coordinate system here. So just to kind of convince you that this does indeed trace out the line, here we'll start with t equals 0. T is at 0, and notice that I'm starting at the point P, and then as t moves forward, I'm going to move towards point Q, and in fact, when t gets to exactly 1, based on this parameterization that I did, I would arrive at point Q. So I want to convince you first that the vector equation that we came up with for what we're after does indeed trace out this line. The problem is that as time goes forward, from 0 moving forward, we're moving in the wrong direction for what I asked. Remember, I said that we want to start at point Q and then end up at point P. So we've got a problem here. We do have the values. When t is 0, we're at one of the points. When t is at 1, we're at the other. But because I deliberately made a mistake, which you will make often, you just need to know how to correct it, I'm going to have to do some adjustment here. So let's return to our problem. So what I was trying to emphasize by showing you that graph is that if I were to pick, usually what you pick for your parameterization, notice this would be 0 less than or equal to t less than or equal to 1. Notice here that when t is 0, I'm at point P. And when t is 1, I would have 1 minus 4, and which would put me at minus 3, and 1 plus 1 times 3, which would put me at 4. So when t is 0, I'm at point P, and when t is 1, I'm at point Q. And I need to switch this because I was asked for the parameterization to start at point Q and end at point P. I could have avoided all this issue if I had been more careful in selecting my R0 and my V, but I want to show you how I can actually adjust this parameterization to fix the problem. What I'd like to do is I'd like to have everything change direction here. So I'm going to go ahead and replace t with the variable s. So let's go ahead and say here, let's let t equal minus s. So that'll be less than or equal to minus s, which is less than or equal to 1. Now what I'm going to do is I'm going to multiply both sides of this inequality by all three sides of this inequality by minus 1. So that's going to give me 0. Careful, multiplying by minus 1 changes the direction of that inequality. And then this is a true statement. 0 is greater than or equal to s, which is greater than or equal to -1. But usually we don't write it that way, so let's go ahead and reverse that orientation to -1 is less than or equal to s, which is less than or equal to 0. So now I have a domain that's going to take everything in the right direction, and I'm going to return to this parameterization, which was going the wrong way, and I'm going to replace the t there with -s. So we're going to say r is equal to 1, 1 plus -s times -4, 3. And so now if I go ahead and distribute this negative sign through to kind of clean this up, we'd have, for our parameterization, r, the position vector, is equal to this vector plus s, multiplying the -1 through, will give me 4, -3 on the interval -1 less than or equal to s less than or equal to 0. What I'd like you to do now is verify that when s is -1, I'm at point Q. So if I were to let s be -1, notice that's going to give me the the vector whose tip is at the point -3, 4. Finally, as the s values vary from -1 to 0, by the time s arrives at 0, I'm now at the vector 1, 1, which is point P, which is where I want to end up with. Folks, you will usually not make this big of a mistake, but I wanted to point out to you the idea of a direction when we give these vector equations, because that's something that is very different than what we saw when we dealt with lines algebraically. We didn't have a direction on the line, but when we have a parameterized vector equation, we certainly do have a direction for which we trace out that line. So just saying it one more time, folks, if I had been more careful in selecting the position vector, and especially more careful in selecting the direction vector, then I would have not have had such a hard time coming up with the parameterization that went in the correct direction. So the moral of the story here, I think, is not assume you'll never make a mistake, but try to, well, when you come up with your parameterization, double check that it goes in the correct direction, and if it doesn't, either go back and correct a mistake, which is probably the best thing to do, or try to modify the parameterization so that it does go in the correct direction. The issue of direction only mattered because I did say the parameterization had to start at Q and end at P. All right, folks, we have one more example. This will be a little bit more straightforward, and that will wrap up the topic of lines. So I'll see you in the next video.